This video is about the self-excited generator. Now, self-excited generator is different from the separately excited generator. Now, this self-excited generator is also one of the types of the DC generator based upon the excitation system. Now, when the field winding, the current for the field winding is supplied from the armature of the generator itself. Now, here the process called the voltage building process is taking place because of the residual magnetism. Now, in the generator principle, we know that in order to induce the EMF, we need the conductor and we need the presence of flux and the relative motion. Now here, when I say about the relative motion, either your conductor should be moving with respect to flux or your flux should be moving with respect to conductor. Now if these three things are present, then there will be induced EMF in the armature conductor. Now in case of the self-excited generators, without giving external supply, you must be wondering how that field flux is created. Now it's because of the presence of the residual magnetism. Though the generator is not working without any field current, the field poles possess some magnetic flux called the residual flux, and the property is called the residual magnetism. So because of the presence of the residual flux, when that conductor is rotating with respect to flux, so it's cutting the flux. So because of that small residual flux, small current is induced in the armature conductor. Now here you have small current induced in the armature conductor, so that small EMF will now drive to the field. Okay, this is field. The small current which is induced in the armature conductor will be supplied to the field. Now on top of the residual flux, now it is adding the small field current. Now because of this small field current, now you have some magnitude here, and then this process is cumulative. Now when it is rotating again and again, like now this process is repeating. Now on, like, it's adding like small current, small field current time and again, and this process is cumulative, and then the generator induced the EMF until it attains the rated voltage. Now this is how the self-excited generator works. Now under the self-excited generator, we have again three types. Okay, three types depending upon the types of the connection of the field winding. Now first one is shunt one. So here this field winding is connected in parallel with the armature, or it is connected across or in parallel with the armature conductor, and have full voltage of the generator applied across it. For example, now let's say if if this rating of this generator is 230 volt, then this voltage is also supplied to this field winding. Now looking at this one, okay, looking at this connection here, now you can derive the relationship between the field winding, field current, the armature current, and the load current. Now here at this point, okay, at this point you have three paths, current paths. One is coming from the armature, and other one is outgoing to the field, and the third one to the load. Now if you apply the KCL at this point, your armature current IA is equal to the current supplied to the field and current supplied to the load. Now this one we are simply applying the Kirchhoff's current law. And then if you want to calculate, if you want to calculate the ISH, okay, shunt current, then it is same as, like, now here we are measuring from this point, this part, okay, this part voltage will be your induced EMF minus the drop at the armature, okay, armature winding. So which means this one will be equal to your terminal voltage. So this terminal voltage at this point you are measuring here where that load is connected. So your field current ISH will be equal to terminal voltage divided by the resistance of that particular field, okay, whatever the resistance it has. Now this one we can also write as E minus IA RA divided by RSH. Okay, now this one is the current and the voltage relationship at the field winding. Now similarly, if you want to calculate the total induced EMF in this kind of shunt wound generator, your induced EMF will be equal to the voltage drop at the armature side plus voltage which is supplied to the terminal at the load plus the brush drop. Okay, as I said, the brush drop is very small for the small generator, we can neglect that one. And okay, now it's the brush drop. If you compare with in case of the small generator, we have to take this one into consideration, but in case of the highly rated generators, so this one will be negligible, okay, comparing to this terminal voltage, so we can avoid this one. Now here we can write that your terminal voltage will be equal to induced EMF at the armature side minus armature drop minus brush drop. So this is the standard formula or the relationship between the induced EMF and the terminal voltage for the shunt wound generator. And from the principle of the principle of the DC generator, we also know that induced EMF is also given by the magnetic flux times number of poles times the speed of the rotor times the number of conductors in that armature divided by 60 times the parallel path. So this parallel path will depend on types of the winding, okay, armature winding. If it is lap winding, okay, your parallel path will be equal to m times p. Now this is the multiplexity of the winding. If it is simplex, you can multiply with 1, duplex 2, triplex 3, and it goes on. And for the wave winding, of the armature, your A will be m times 2. So again m is same as here, okay, it's the about the multiplexity. Now in next video I'm going to discuss about the series wound DC generator and compound, okay, wound DC generator. Okay, thank you.